and I just posted the video. Let's recall that. So we're going to always assume that H is independent of time. Time-dependent Hamiltonians really ought to be the subject of a whole nother class. At least that's what I experienced. We had to take a second class after this class on time-dependent this and that. Okay, so whenever we're solving the Heisenberg equations of motion, and again, remember how this is derived, it's really not that bad. Now, as we had originally derived it, the Hamiltonian, you don't know necessarily, well, the way we derived it, the Hamiltonian was time-dependent. But for various reasons, by definition, we'll just say that it's not. Alternatively, you can also say, and don't write this down, remember that if we're going to do this, this only works if the Hamiltonian is time-independent. So we're in a time-independent class, let's put it that way. Okay, now the thing that slays me, the hard part is that as this is written, this is undoable. Because we're going to, we need to have something to the right that we're then going to do some integration on the left. We're going to bring dt over and integrate this and integrate dp. But that means I have to know what this is. It can't be left as this nebulous squiggle of lines. And so the answer, of course, is, and I showed you how to do this, it's fairly unpleasant, just a bunch of lines. It is 100% exactly true that the time-evolving operators can be factored left and right. And then you know what this is. So now I have to tell you, of course, we were doing a free particle Hamiltonian, so there's p squared over 2m. And again, one of the reasons I stipulate that this is time independent is that for this to change with time would be kind of nutso. It's like saying kinetic energy is 1/2 mv squared at time 0, and that at later time it's something else. And that's like, no, that's weird. No, that makes no sense, right? Okay, so in this case you get 0. And I'll just bring the dt over. When you integrate that, it's still 0. So therefore you get p of t is 0, which is what we've always known it to be. And on your exam, what's really cool, on your exam, what you have is I give you a wave function, the standard wave packet thing, and you're going to Fourier transform that using the formulas I already gave. If you're a little concerned that you didn't write it down right, let me know. I'll just write it. I didn't write it down in the homework question because exam, because I kind of wanted you to force you to go through your notes. So it's one of the things about exams that people forget the value of it is to make you go through your notes. Anyway, the momentum, so when you're doing average momentum, and so in this case it's time, the time dependent expectation value is not time dependent. Anyway, I just want to point that out. So this is kind of stupid the way I wrote it. Remember that that's actually this. And of course, if it was position, it's just x. And so you integrate one of the things, remember, defining I in Mathematica is a bit tricky. And then in Mathematica, to make a derivative, you just got capital D bracket in the function. Okay, and again, in Mathematica, that's not hard. But if you are in the P representation, so this is what I had you do, it ends up being this. So it's just like x, right? When you do the average value of x, you just integrate the wave function squared times x. When you Fourier transform this thing to p, it's just the integral times p. It's really, really, really easy. So anyway, I just wanted to point out that that's one of the values of working in momentum, is that, we always think of position as being kind of easy to work with. X is relatively easy to understand, and we hate derivatives. And then that gets flipped over in momentum space. P is the easy guy, so you literally are just typing that into Mathematica and hit go. And the position operator in momentum space is IH bar plus DDP. Anyway, so, and we went over that before. It's pretty, I make that pretty clear in your exam. Okay, anyway, so now we have to do the position. And this is where it gets a little bit more interesting. And I'm just going to do this from memory. I think I remember how to do this. Right. So again, the thing that always slays me is making certain that I don't get confused what's time dependent and what's not. Okay. Now, in this case, those operators, the unitary time revolving operators and its adjoint, those are going to do something. Okay, and on the homework, sorry, on the handout, I gave you a handout. It's in the textbook, blah, blah, blah. Let's factor the 2m out, it's a constant. What you end up with is this ends up being just, I said this last time, it's in your textbook, it's worked out in the handout. When you have position and a function of momentum, it's just the derivative of the function. And that's nice, handy, you can either just remember that, it's in your textbook, I'm telling you now, or if you want to explicitly work through the commutator of x and t squared, again, on the handout, I do it in its raw form, where I write out the commutator, I apply a wave function, a dummy wave function, I let it do its job, and then I divide out the wave function, which ends up with is p. And now I've got unitary operator, p, unitary operator. So it's p of t. Right?
It should be 2p, the derivative, right? It's p squared, the derivative is 2p.
Yeah.
Oh.
So then the 2's cancel.
Yeah.
I was going to say, or else my number 5 is wrong.
Oh, well, I would have worried about a little factor of 2. Grad school, the thing is, if you're writing a program, you're going to write a paper. So I have a few papers on quantum dynamical, mixed molecular mechanics, quantum dynamics when I was a grad student. Factors of 2 are not acceptable. If you get a factor of 2 where it shouldn't be, then your results are wrong. However, when we're doing these things in class, I'm going to let that slide. I let it slide for myself. But when the you-know-what hits the fan, make sure you get it right. If this is going to be in the paper, get it right. But if you guys are missing a minus sign of factor 2, I'm not really concerned about that. Anyway, okay, so we find this, but now you see on the exam, you're going to notice as I'm doing it here, I solve these in a particular order because I know ahead of time what the best order is. I solve P of t. I solve P of t first because guess what? It comes back here. Is that right? Is it minus or plus?
It's minus.
Is it minus?
It's a minus. where did I go wrong? Where did I go wrong? No, the commutator is positive, isn't it? No. What have I got? What is wrong with me? Of course it's plus. You know what I'm... Jesus. Sorry. Right, so when you evaluate it, normally you don't think about that. So, again, regular old x, what we're solving. 0 to t. Remember, you always have to make the limits, when you're integrating both sides of an equation, the limits have to speak to each other. They have to be self-consistent. No. I have an IH bar here, don't I? Sorry. It's the derivative times IH bar. Yeah, definitely there was something wrong. Yeah, sorry. So, as I was bragging before, I can do this from memory, apparently not. Okay, there we go. Sorry about that. Okay, so there you go. So I'm just walking you through it because, taking my time unlike last time where I'm rushing because I'm always jabbering too much. So anyway, there you go. Okay, now again, on your exam, when you get to this point, because this is part B, in part A you solve this, but you won't get this, by the way. I threw a little monkey wrench at you. It's not hard, but it won't be this simple. So you'll get something a little bit more complicated, and then you'll just integrate. It will just be slightly more complicated than just P, with no T's in it. So the integral of dt, the integral with respect to T won't just throw up a T, it'll do something slightly more complicated. If you have like a T in it, then it'll be 1/2 T squared, right? Yeah, so anyway, look out for that. So anyway, what you're going to do on the exams is identical to this. This is why I'm expounding upon it so much. But there's just a little bit of a monkey wrench in it. Okay. Anyway, now here's another neat thing. There's a couple last things I want to talk about before we go to harmonic oscillator. Let's see what I want to mention. Okay. So we're just mopping this stuff up. I want to point this stuff. Zero or not zero? We're doing 3 parts. Huh?
15.
You said that x of t is equal to x naught. Wait, you said that and it's not 0.
Right.
Wait.
X does not commute with P.
Yeah. Easy.
This is not 0. In fact, you can figure it out. It's okay, this is always relatively easy. At this point, I hope that you can look at this and just kind of figure it out. Remember that, so you're going to multiply these times each other and subtract the multiple but reversed. You're going to end up with x squared minus x squared. So this guy never does anything. When you have a function in itself, it's going to be 0. So what you're going to end up with is the commutator of p of x, which is going to be, if it's p first, then it's IH bar. It ends up being IH bar minus IH bar. Yeah. If p is first, then it's minus IH bar. If x is first, it's IH bar. Anyway. Okay, that's not 0. So, the position operator does not commute with itself. That means that the wave functions are not, they're not the same, right? So remember that when things and operators commute, they share the same eigenstates. When they don't commute, that's not true. So this is one of the examples of why commuting or not commuting is a major, major deal. So we think of all our wave functions as being friendly and easy to work with, but over time, you're using the wrong wave functions. Uh-oh. So anyway, I just wanted to point that out. Also, so that means, therefore, let's not worry about working through this. So the product of the two variances has to be greater than or equal to the commutator, right? Squared over 4. Remember, it's the absolute value square over 4. So it's greater than or equal to, the variances are greater than or equal to the commutator squared over 4. Absolute value, anyway. Okay, now what this also means, now again, one of the things that gets lost a lot of times is that uncertainty principles do things. So what would happen is, let's say I've got myself a wave function, and remember that the Gaussian wave packet is a Gaussian. Over time, this means that it has to broaden. For the uncertainty to increase, the wave function has to broaden. So when you put a Gaussian wave packet on a flat surface and let the damn thing start evolving in time, which I will have you do on a problem set using a computer, I'm going to show you how to do this calculation. And trust me, it's absolutely fantastic and fun to watch this little thing start moving around. You can put it in a harmonic potential. You can watch it go back and forth. You're going to do it later. It's really fun. So anyway, if you put it on a flat potential, it just starts to flatten out. And that just means that you don't know where the particle is. So that tends to be kind of important in a bunch of stuff.
I think the commutator is minus IH TM plus IH X into them. Then one more thing. Then one more term, right?
What?
This minus IH H bar P or M.
Yeah.
Plus something will be due, right? Because one will be IH minus IH bar double reduction of X. So that is minus IH bar. Plus then there will be X into P of X. There will be two terms, right?
What, this commutator? That's 0.
No, the next one. So X to P. So the one will be X to P and there will be P to X, right?
What? I have no idea what you're talking about. I'm fairly sure I'm right about this, right? So X commutes with itself, so it's only P and X.
Yeah, then first one will be XP, next one will be PX, right?
Yeah.
Yeah, so then the X will come in front of the...
No, you've forgotten. No. If you work through this, Px minus xp is I minus IH bar. That's it. Right? Yeah. Minus IH bar. The T over it. Right? We've done that. Right? It's a little complicated, but anyway. Yeah. Okay, so with that, I just wanted to point out that there's this thing called, I don't want to go over it because I just don't see it that much. It's called our Ehrenfest Theorem. And all it is if you have a potential, then what you're going to find, here, let me just put down the sampling features without necessarily solving it. Again, assuming that this deal is time independent. So we've already worked out what to do with this, but if you then, actually I don't think I put a little hat on B. If you have a potential energy term, it's going to get a little bit more complicated, and that's because momentum, the first step here, the momentum will not, you're going to have a px commutator, right? So with no position in the Hamiltonian, notice that the commutator ends up being 0 because you have p cubed minus p cubed, which is 0. But if there's an x in here, then you're going to have a px minus xp, and that's not 0. So this is going to complicate it. Anyway, so what I want to point out is, let's see, what you'll find is, you're going to find this relationship if you work through the commutator, you're going to end up basically with just, d, here, let me just remind you that, just writing down what I've already said. Okay, just like here, I mentioned to you that if you bloody work through this, you find that you just get the derivative of p, of the function, sorry, you get the derivative of the function. Or it turns out that it will always be. When you have x in a function of p, it's always just the derivative of the function. Likewise, when you have p and x, it's just the derivative of x. So, and that's in your book. It's just tons of algebra to show that, and I'm so long-winded that I really don't want to go over that. So that means that, therefore, you can do this. If you take the double derivative of position, then the time evolution, so you're basically time evolving the derivative. So the derivative, so you're doing this. Now, of course, we know that the time derivative of position, we've already worked through this. We just did it. It's p0 over m, which is the time derivative, right? So, look, this kind of makes your head spin. So I just want to point out, let me just walk through this again. The derivative of the derivative is going to be 1 over IH bar, the thing you're taking the derivative of, which is the derivative. That's the only part where it kind of like messes with you. Oh, it's a cat, forgot the cat. Now, we've already worked through that this guy is P is momentum over mass, so that doesn't change. If you tack this on, that doesn't change. I didn't want to work through that. It doesn't change. But by definition, 1 over IH bar operator commutator with H is the time derivative of that operator, right? But I just solved this. Okay, so what you end up with is which more generally you can just call it minus del squared. Minus del? No, minus del. And if you want to, of course, if you want to do expectation values, then you can just insert that apparently without any, you can just do it basically. Is that right? Yeah. And that's Ehrenfest's theorem. Now, apparently, now, I believe that this is basically one of the standard Newtonian equation, if I'm not mistaken. And another thing that apparently has people kind of PO'd about this is that there's no H bar in it. And so this is not quantum mechanical. So my understanding, I remember in my class or somewhere, I remember someone saying that Ehrenfest's theorem is like questionable. And I don't remember why. But I do know that there's no H bar in here. And that basically should never happen when you're doing quantum mechanics. That's like impossible. So that is a red flag. Yeah, look, I just worked, I mean, I don't think there's really anything wrong with what I just did. So I tried to look that up before class and I couldn't find anything. But anyway, I do want to let you know that that's out there. It's something, you know, one of the things I hope to help you out with is tell you what's in your future because I've already lived it. I don't know that when you know, of all the probably 1,000 PChem seminars I've attended, Ehrenfest's theorem, I think, has come up like once. Just like I mentioned that Dyson series thing for time evolving, to time evolving Hamiltonian. I've only seen that once. So I don't see it come up that often. But anyway, I just wanted to let you know that that's what that is. It's kind of a funny little derivation, but it's not something I think is, not to my knowledge, it's not something you really need to worry about too much. Anyway, so there you go. That's all there was on that. Okay, to hopefully, you know, get some progress in your general education, I can tell you that this next subject is to revisit the harmonic oscillator. This is important. As much as I just mentioned this Ehrenfest thing, I just don't see it very frequently in papers or talks. But what I'm about to go over, it is incredibly rare for me not to see what I'm about to show you. So this is terribly important. Now, a lot of you are solid state materials people, so you know, molecular vibrations are terribly important, especially if you end up being an FTIR person. They're important for all kinds of reasons. It's thought that electrons, when you shine visible light or UV light on something, it gets electronically excited. And it's thought that the vibration, that electron relaxes to the ground state by vibrationally exciting things. So vibration is terribly important. So I want to visit the harmonic oscillator. Now the damnedest thing is, though, the way you do the harmonic oscillator problem in grad school is completely different than undergrad. So that's kind of donko nutso, but there's a good reason for it. So anyway, that's the big picture. We're going to revisit the simple harmonic oscillator, and I begin that with an S. And you know that this is the case. And we'll do time dependence on it. So just for now, just assume that I'm not doing time dependence. Hooke's law. No, that's not Hooke's law. Hooke's law is force is minus spring constant times x. And then this is, actually I think it's this. Right? What is that? That's acceleration? Oh, anyway. Potential energy of a spring. Right? Okay, now remember, I told you this before, and again, horribly important. Okay, so p squared is minus h bar squared over 2m, double derivative. And remember that you will not see 1/2 kfx squared. You always see this. So what bothers me is that sometimes when I see the harmonic oscillator expressed using that terminology, sometimes I forget what I'm looking at. And M is usually like a reduced mass. So, right, if it's H2, then the mass is actually like half of an actual hydrogen atom. So don't forget that. We tend to assume that you're confident enough to know that mass actually means the reduced mass of a like a diatomic or whatever we're talking about. Okay, so anyway, just want to remind you that. All right, now, as undergrads, what I do is, at this point, I've hopefully, maybe I'm fooling myself, but I hope that I've gone over the fact that you got yourself a differential equation. This times a function is equal to energy times a function. It's a weird-looking mathematical entity. It's not hard to understand the parts, at least. And the whole of the solution being defined as the function that satisfies this, was solved by a 17th century mathematician, and good for them. They solved these problems just for the hell of it, because they could. And you get basically a Gaussian. Whoop-de-doo. And what is the constant? It's an eigenvalue equation. And you figure this out. They didn't have all these constants. But it's not hard to insert that. And you find that there's an infinite number of solutions, which we know to be, the first one is a ground state, the next are excited states. So I usually spend no more than one lecture at an undergrad level just saying, here's the problem, we're not in math class, I'm going to give you the solution, and you plug the solution back into the problem, you get the eigenvalues. This is how vibration works. Now let's go to rotation. That's what I do in undergrad. So what the hell is there to talk about? Right? There really isn't much to this. Okay, it turns out that you redo the problem in a completely different way. And don't write this one down. This is something I probably should have brought up before. For some of you were messing with this on the homework, which annoyed me because I didn't want you to, because I wanted to bring it up here. You have this raising operator, which can take the spin down state, the minus state, and turn it to the plus state. You may also recognize that as this. And if you apply it to the minus state, you get the plus state. So however you want to work that, there's also the minus state, which would turn that to nothing. But if you apply that to the plus state, you get the minus state. Okay, so there's this whole class of operators. This is called a ladder operator. What it does is it turns ground states to excited states and excited states to ground states. So what? Well, if you read the textbook, and if you didn't, that's fine. You can sometimes turn other operators that are a little complicated into these operators. Sometimes it's just kind of neat to do it. Sometimes there's more you can get out of it, which is what is the point of doing the harmonic oscillator with its own ladder operators. So ladder operators are different, obviously. Spin is ultimately very easy. But what you do is you're going to redo the harmonic oscillator with ladder operators. And it's because you're going to find relationships using ladder operators that are obscure otherwise. There's all kinds of neat things are very transparent when we redo the harmonic oscillator with its ladder operators, which are, where are we? Annihilation. Okay, so this is S minus, and that gets the letter A. Now, the book does something kind of hideous, which is it makes the creation operator look like the adjoint, which it is not. Anyway, I'm getting there. Now, as for how anyone figured this out, I have no idea. Okay, then you have the creation. Okay, now look, I will, there's no avoiding this. But I put a little star by it. If you look at the book, it is a different type of star than the cross. It's like a star versus a cross. The cross is for an adjoint. Adjoints work on bras. Operator adjoints work on bras. Operators work on cats. This is not the adjoint, I think. This is not the adjoint. I'm pretty sure. And if you look carefully, the symbol is different in the book. But it's so subtly different. There's like a little, it's like a dagger instead of like a straight up cross. It's a cross that kind of looks like a dagger. So be careful with that. Okay, anyway, it's just a little bit of funkiness. I think they should have been a little bit more thoughtful about the symbology employed. Anyway, I need to double check if that's correct. I'm pretty sure though. Yeah, I'm pretty sure that that's the case. That the creation, I don't think that that's the adjoint. It's just a different operator. Another thing to point out about these types of ladder operators, one of the things the book does, and it's really subtle, it never uses the descriptors it uses for other operators, like the eigenvalues. Oh, okay, these are operators. Well, they're eigenvalues. Who cares? They don't work in any eigenvalue equation. I mean, look at this damn thing. Look at this. What kind of eigenvalue equation can I make work with this? How can I get this state equal to a number times the minus state? I can't. Right? It's just, so you don't even talk about that. You don't call it Hermitian. You don't talk about its eigenvalues. You just drop all that. These types of operators, they're not Hermitian. They're just whatever they are. But they don't, anyway, they're completely different. And it's just kind of interesting to me that the book just never mentions any of the normal operator stuff like eigenvalues and what's its basis. None of that applies. So anyway, just heads up on that. So these are just very different types of operators. Okay. Now let's see. Oh, I have just enough time to do some things with it. And so what the heck do you do with this? Okay, so I'm gonna just show a relationship with this. Let's see, that's this one, and then I have, and again, I'm writing really small, I don't know why. And then of course I subtract and permute. And so minus comes first, and now I have plus. And a bunch of algebra later, not that it's really that bad, so I just factored that out. A bunch of algebra later, what you get is, it's not really that bad. If you actually just stare at this, you can get it. Here, let me factor out a minus I. I'm gonna do two sets of algebra at once. What you're going to end up with is a commutator, and then you'll actually notice that you get the same commutator again. So, anyway, let's see. It's like the x squareds will disappear. The p squareds, when you FOIL these out, the p squareds, those will actually cancel. The reason that anything is left over is that xp is not the same as px, right? So that's why that's going to work out the way it does. And so what you end up with is minus I over h bar. Xp is IH bar. Minus I squared is just 1. Okay. Okay, now the reason this is important, so the commutator is 1, and then there's this new operator. And I'm going to call it this. Remember that, if I multiply 2 operators, it's a new operator. I'm going to call it the N operator. Annihilation times creation. Oh, creation times annihilation, sorry. And what this ends up being is I am going to go ahead and do a lot of factoring. You can actually, it would actually be this one, right? X squared, then I'm going to end up with a plus p squared. And I'm going to have that mw squared, so minus I squared is plus mass frequency squared. Okay, yeah, that makes sense. In this, right, that's the same, that makes sense. Okay, then I have, again, it's just this one, right? Then I have the cross terms. And of course, this still factors out. And it will look like a commutator, which, by the way, we already just worked out, which is 1. All right? So again, it's just creation annihilation, which is actually this one here. Just FOIL it out, you get 4 terms. I did some factoring. It's just that you may notice that this guy right here, that's the Hamiltonian. This one, and the next one is yeah, look at this. The M frequency factors cancel. You have to just factor out an I, and then you get XP minus PX, right? And this ends up being plus 1/2. Because that's IH bar, and I squared, that's minus. It's minus, right? Okay. And I know I'm out of time, but I'm done. Let me show you why that matters. Why that matters. Okay, I got N plus 1/2 wait a minute. No, it's not. Where did that H? Sorry. Yeah, there's nowhere for that H. Sorry, I just wrote down M and then H bar. Sorry about that. God, it's right there too. Sorry. Okay, so N plus 1/2. So you can see that that's it. This N operator reports the quantum number of the harmonic oscillator. Yeah.
It's the degeneracy equation, right?
Huh?
It's the degeneracy equation. The H bar nominal will be energy, right?
Yeah.
The degenerate equations.
Yeah, because right, it just you can operate on the state on the wave function, and it tells you like if it's ground state at 0, and then the eigenvalue is H is 1/2 H frequency.
1/2, yeah.
Yeah.
It's a different way to get there.
This is right. It's just a different Hamiltonian. So now, what that allows us to do, though, is figure out the eigenstates of this operator. So it's another way to do it. But now, big picture. Vibration appears in every quantum mechanical problem because you can't avoid it. And when you're at a graduate level, you will never see this done any other way than except with the creation and annihilation operators. You will see these the rest of your life. That's why I want to go over it. Probably be able to finish this up mostly tomorrow. But anyway, definitely you've got to see this. That's like one of the worst things for you not to know about this. But here we are.
You can